Okay, so today we're going to look at 3 different descriptions of a chemical reaction. We're going to classify them first because this will allow us to predict the products. And then we'll look at the states of the reactants and products just to make sure that they match up with the type of reaction we chose. And then the last thing we're going to do is we're going to balance the reaction equations. Then in the second part, we're going to use stoichiometry to predict the amount of product that should form from a reaction and compare it to how much actually forms, because no reaction is 100% efficient. Some always is left behind. All right, so now we're going to look at chemical reaction 1, and here we've got a beaker of cobalt 2 chloride, which is CoCl2, is dissolved in water, which means it's aqueous. And then we have sodium hydroxide, so that's Na with a +1 and hydroxide with a -1, so we get NaOH. And that's also dissolved in water, so it's aqueous. So here are 2 reactants and their states, and now we're going to try to predict the products by classifying the reaction. So we need to know the major types of reactions before we do this. There are 5 major categories. The first one is synthesis, and here we have A plus B gives us AB, or we always form one product. Then we have decomposition reactions, where we have something breaking down, so AB goes to A plus B. Then we have combustion, which is a hydrocarbon, CXHY plus O2 gives us CO2 and water. A single replacement, which we have a metal plus an ionic compound, a metal and a nonmetal, forms MX plus M, and then double replacement where it's 2 ionic compounds and they switch partners. So the description also agrees with the fact that this is a double replacement because we've got 2 ionic compounds here, and we're going to form cobalt 2 hydroxide and sodium chloride. And the description also agrees with the fact that this is a double replacement reaction because we have 2 solutions with ionic compounds dissolved in them, and then a solid forms in the end. The other ions stay dissociated, and now we need to figure out which one is the solid product, cobalt 2 hydroxide or sodium chloride. And to do that, we'll look at a solubility table. All right, so now here we're going to decide which is solid. Here we've got hydroxides are insoluble, and group 1s and chlorides are soluble, so there's our solids and insolubles. So here's our balanced equation. Cobalt chloride aqueous plus sodium hydroxide aqueous gives us cobalt 2 hydroxide solid plus sodium chloride. And now underneath, I'm just going to write out the names. Now let's go to balancing the equation. All right, so now we're going to balance our equation, and on the left are the steps, and on the right I'm writing the equation, or the skeleton equation, the equation without the numbers. And there's a few things we're going to look at before we start balancing here. First, we're going to look at the subscripts, which are the little numbers there, then the coefficients in front, and then the coefficient times the subscripts gives me how many atoms, and if there's no number, it's a 1. So there's lots of 1s in this one. Then we're going to start with the first element. 1 times 1 gives me 1 cobalt on the left and 1 cobalt on the right. And then we're going to jump to our hydroxides. 1 times 2 gives me 2 hydroxides, so I need a coefficient in front of NaOH, which is going to be 2. And then this means that I have 2 sodium on the left, so I need 2 sodium on the right, so I'm going to add a 2 in front of NaCl. And then this means I have 2 chlorines, and I already have 2 chlorines on the left, if you can see. And so our equation is balanced. All right, so let's look at our chemical equation 2 here, and we've got liquid butane is lighting up, and this type of reaction is combustion, and here's how we know. So again, we know synthesis is A plus B gives us AB. Decomposition is AB breaks into A plus B. Combustion is a hydrocarbon, CXHY plus O2 gives us H2O and water, or CO2 and water. You can say it either way. Single replacement is a metal plus an ionic compound, and the metal switch places. And then a double replacement is two ionic compounds, and again, they switch places. The description here definitely agrees with a hydrocarbon burning in times of oxygen, because butane is a hydrocarbon, so that's how we know it's a combustion reaction. The description also agrees with a combustion reaction. It mentions a blue flame, which means that lots of energy is being released, and in a combustion reaction, they're always exothermic. Exothermic means that energy is released. Now, this is why we use combustion reactions all the time. It's where we get all our energy to make our cars go and to light up our houses. And it also says there's nothing left afterwards. And this also agrees with a combustion reaction because of the fact that the products are odorless, colorless gases. And so all of this leads us to believe it's a combustion reaction. And now we're going to predict the products based on the general formula of a combustion reaction. Now, predicting the products for a combustion reaction is pretty easy if we just look at the general formula for a combustion reaction. So that is a hydrocarbon plus oxygen gives us CO2 and water. So we're going to produce CO2 and water here, and then I'm going to write out what everything is. C4H10 is butane plus oxygen gas gives us carbon dioxide plus water. And now it is time to balance it. All right, so these are a little tricky to balance sometimes, so we're going to walk through this slowly. Again, we've got our butane, which once released from the lighter is a gas, plus oxygen gas gives us CO2 plus H2O, both gases. We're going to look at our coefficients and our subscripts again. Remember, coefficients times subscripts gives us the number of atoms, and then we're just going to start from the carbon here. 1 times 4 gives us 4 carbons, so I need a 4 in front of CO2. Then I'm going to look at oxygen. Actually, I'm not, because remember, this is our split element. It's there twice on the right, and so we're not going to do that one yet. We're going to move back to the hydrogen on the left. So we've got 1 times 10 gives us 10 hydrogen on the left, so we need 10 on the right. So what times 2 gives us 10, and of course that is the number 5. Now here's where it gets a little tricky. We're going to balance our oxygen, our split element. So we're going to look at the right-hand side, and we've got 4 times 2 oxygen plus 5 times 1 gives us 13, which is a weird number, right? On the other side, we've got what times 2 gives us 13, and of course, it doesn't work. Anytime I end up with an odd number of elements, we're going to, and it has to be even, we're going to double that C2H4 and start all over again. So let's do that right now. So here now we're again starting with 2C4H10, and now we're going to balance it again. So I've got 2 times 4, which gives me 8 carbons. So what times 1 gives me 8? And of course, I'm going to throw an 8 in front of that CO2. And we're not going to balance oxygen yet, remember, because it's a split element. We're going to move back to hydrogen first. So we've got 2 times 10 equals 20 hydrogen. So I need to get 20 hydrogen on the right. And of course, what times 2 gives me 20? And it is 10. So now let's try our oxygen again. We've got 8 times 2 plus 10 times 1, and that's going to give us 26 oxygen. So what times 2 gives me 26? Now it is 13, and this equation is balanced, and we're all set. All right, in our third scenario here, we've got copper wire, which is a solid, is dipped into an aqueous solution of silver nitrate. And now we need to figure out the type in order to predict the products. Again, we've got synthesis reactions, which are A plus B gives us AB. Decomposition, which are AB, goes to A plus B. Combustion, which we just saw, a hydrocarbon plus oxygen gives us CO2 and water. And then we've got single replacement, one metal reacting with an ionic compound to kick one metal out, and then we get the other metal by itself. Double replacement is 2 ionic compounds that are switching partners here. And so what we're looking at is Cu is a single metal by itself, and silver nitrate is an Mx, so this is a single replacement. And the copper description is also agrees with what happens. We've got copper kicking silver out of solution to form solid silver, which is the fuzzy bluish white solid that forms, and the solution also turns blue, and copper solutions often turn blue. So now we know what is forming here, and we can start writing out our balanced equation. All right, so we know copper goes in and kicks the silver out, and it's going to bond with nitrate. So we got Cu, which is +2. Now copper has two charges, 1 or 2, but 2 is the more common one, and that's why I'm using it here. So we're going to take Cu and crisscross it with our nitrate, which is -1. So we end up with CuNO3 2. And we know this one is aqueous because it gives us a blue solution in the end, and blue solutions are copper solutions. So I'm going to mark this one aqueous. And then we end up with Ag solid, and we know this again because of the description. They give us it's a nice white silvery solid, and that is our silver. So let's just look at our full balanced equation. We've got copper solid plus silver nitrate aqueous forms copper nitrate, copper 2 nitrate aqueous plus silver solid. And here's the words underneath. Copper plus silver nitrate gives us copper 2 nitrate plus silver solid. And now we're going to balance our equation. We're going to kind of walk through and look at the subscripts and the coefficients. So again, our subscripts are our small numbers. I'm going to circle them. Our coefficients are what go in front, and coefficient times subscripts give me the number of atoms. And just remember, we're going to balance our nitrates together. So let's look at our coppers first. We've got 1 on each side, and then I've got 2 nitrates on the right, so I need 2 nitrates on the left, which gives me 2 silvers on the left. And then I'm going to put a 2 in front of a silver on the right to get to 2. And now we are all balanced. Now we're going to use stoichiometry to predict how much will form of a compound as compared to what actually forms, since no reaction is 100% efficient. And you can see here we have 10.6 grams of carbon dioxide formed. And so what we need to do here is figure out how much is actually formed as compared to that number. All right, so to figure out which one runs out first, because we have 2 different reactants here, the C2H3Cl or O2, we need to take both of those grams, and we will predict both 2 grams of CO2 using stoichiometry, which is really using the balanced equation to get from moles of one thing to moles of another, and then to come out of moles or into moles using grams. So we're going to start with our 10 grams of C2H3Cl, and we're going to multiply that by 1 mole of C2H3Cl over our molar mass from the periodic table of 64.469. Then we're going to use the balanced equation to get out of moles of C2H3Cl and into moles of CO2. So I've got 4 moles of CO2 for every 2 moles of C2H3Cl, and then we're going to multiply by the molar mass of CO2 to get 2 grams of CO2. So this first one predicts 13.6, and we're going to round it there because of significant digits. And they're going to repeat with O2. So we've got 20 grams of O2 times 1 mole of O2 over 32.998 grams. Then to get rid of moles of O2, I'm going to put it on the bottom, and that's 5 moles of O2 multiplied by 4 moles of CO2. Again, those numbers are from the balanced equation. And then I'm going to multiply by the molar mass of CO2 to get into grams, and I get 22. I write it wrong at first, 22 grams, and we can tell that 13.6 limits our reaction because it's a smaller number. So now we can compare what we predicted, 13.6, which is what we call our theoretical yield. So that's how much this reaction should produce if it's 100% efficient, which no reaction is. So we're now going to compare it to how much we actually got, which was only 10.6 grams. So what we're going to do is we're going to look at the percent yield equation, which is equal to the grams from the lab, which is our 10.6, divided by the grams from our calculations, which was 13.6, and we're going to multiply by 100 here, and we're going to get a 77.9% yield.